optimizations, right? So we talked about how to overfit. Now we're saying, okay, what if we wanted to make our neural network faster, stronger, and better, right? Way we can do this is doing some different stuff. So I mentioned a little bit before is that a lot of times in machine learning, it feels like black magic. We're just like, I don't know, change this, see what happens, right? And a lot of times that will, like, I think even people who are in the data science field will kind of do this approach to like, I don't know, try this and see what happens. This is kind of a pretty typical viewpoint. I will say there are it is very difficult. Even if you're an experienced machine learning engineer and you build a neural network, you probably won't get the right hyperparameters the very first time. That is very typical. However, you can use some kind of like general idea of how to get this stuff done. In general, I would say using research that's already been done. You could technically try to do this yourself and like see what works best. But in general, there's some general guidelines that other people have researched. And this changes every few years too, because as we improve more and more and more and learn more about how these things work, you see like, oh, well, this optimization works better than others. Okay. So here's a couple documentation. I think this is also listed in the curriculum, but if not, it's in this repo. So one problem we're going to come across is something called the vanishing gradient problem. And in the vanishing gradient problem, sorry, just get rid of that. There you go. It's not the vanishing gradient problem. The problem is that basically the gradient gets really, really small. Related problem is an exploding gradient problem where the gradient gets really, really large, okay? And one thing in particular in this vanishing gradient problem is basically slow training. Things just take a long time to improve because basically the gradient's so small, it can't really change it that much. We also get into something called a local minimum, right? Is our local minimum basically, we're on this little, small little, what's it called? Valley in our cost function, right? And in that cost function, we're in this little valley, but we want to get into the better valley. So if I were to kind of quickly draw this out, your cost function might look like in 2D like this. And then we want to be as low as possible. And this is like, that's where we want to be. This is like gold star right here, like perfect model, awesome. But if we're in here, the model's like, hey, this is pretty nice. Like I'm just kind of chill out over here. So we want to get out of this part. So this is actually a great analogy of like hill climbing or trying to find the lowest point. We'll use different strategies to get out of this point. So some ways we can do this. First one is activation functions. So remember what activation functions do. What they do basically is they take a value and say, hey, like, are you like, am I going to let you pass through? I'm going to kind of scale you down. What am I going to do with you? So you can kind of think like, for example, RayLu is going to say, if you're less than 0, you ain't doing anything. We're not going to go there. If you're negative, you're just 0. Like you're not going to change, right? So this is a slight problem is that one of the things that might happen is that if you're in the negative, you're like really negative, you're just going to stay 0 the whole time. You're not going to change from that point. You can also get to this point where they're saturated, where basically there's not much improvement on the other side. This will be closer to like tangent H. So in general, and there's a whole bunch of research, like I'm gonna make this really clear. There's a whole bunch of things you can do. And I'm pretty sure like there's activation functions that we haven't even talked about. But in general, RayLu does a pretty decent job. This ranking is more or less pretty true. In general, RayLu is pretty consistent, but like leaky RayLu tends to do like the better performer. It tends to do models a lot better. There are technically these other like exotic neural network activation functions. One example is like the exponential linear unit. And so it's kind of like a playoff of the leaky RayLu, but basically it has an exponential. There's other things in there that I won't get into. I would say do your research, but in general, I would say never use sigmoid. Sigmoid is basically outdated since 2000. You know, it will do all right, but you'll tend to get these parts where it just doesn't train any better. RayLu is a pretty good balance of speed because it's really simple. Remember, it's just basically saying it's just going to be the same value. It's going to be that linear part, or it's going to be 0. So it's really quick to train. And most systems have optimizations that purposely use RayLu in their packages, so tend to be really quick and speedy. However, note that sometimes you're not going to get the most optimal model. In that case, if you're really trying to get that optimal model, you'll have to spend more time training it with a leaky RayLu, but they'll tend to give better results. But in general, I would say RayLu is a good first start. And I would say only using leaky RayLu and other exotic parts if it's really necessary. And of course, it just depends. Okay. All right. All right, I'm seeing I have about a minute left. So tell you guys what, would you guys be cool if we kind of continue this on maybe next time then we meet up? I'm actually sure, yeah. I can talk about these next parts. I don't want to just go through them really quickly. Random starts and then momentum. Yeah, how do you guys sound about that? Sounds like pretty cool. I'll stop recording here then.